For millions of years, a colossal star has teetered on the edge of survival. HR 5171, a yellow hypergiant so vast it challenges our understanding of stellar limits. With a radius more than 1,000 times that of the Sun, and a companion locked in an intimate, unstable embrace, this star is shedding mass, expanding outward, and rewriting what we expect of dying giants. Today we explore what drives this star beyond the bounds of stability. If you enjoy venturing to the extremes of the cosmos, please like, subscribe, and share, and tell us in the comments, what would you ask about a star so immense and unstable it may unravel before our eyes? Thank you for watching. Now let's begin. The Milky Way is a large disk galaxy with a bright central concentration of stars and a wide thin disk of gas dust and starlight that wraps around it. From far above the plane, the galaxy appears as a flattened spiral with several arms curving out from the inner regions, each arm tracing where gas and stars gather more densely than in the surrounding space. Within the disk, many hundreds of billions of stars orbit the center along paths that are close to circular, while clouds of gas and dust drift between them and slowly change shape under the influence of gravity, pressure, and rotation. In this structure, the star known as HR 54131, A belongs not to the inner bulge or to the sparse outer halo, but to the actively star-forming disk where gas remains dense enough to build very massive stars. The disk is much wider than it is thick, so most of the young and middle-aged stars sit close to a single midplane, embedded in a layer where gas and dust also concentrate. Above and below this layer, the density of stars and gas falls off, and the environment becomes more diffuse and quiet compared with the busy midplane. The hypergiant, as an evolved and very massive star, still occupies this thin, crowded layer, sharing its general motion around the galactic center with many neighboring stars. The spiral arms of the Milky Way are not solid structures, but gentle patterns in the distribution of material. As gas orbits the center, it passes through these patterns and experiences mild compression. Where the compression is strongest, interstellar clouds can collapse more readily into denser clumps, and the rate of star formation increases. Over many millions of years, this process leads to bands of young clusters, bright ionized nebulae, and pockets of dense clouds that outline the arms. Between the arms, the gas is more diffuse, and fewer massive luminous stars are present. The arm that matters here is the Centaurus arm, a major spiral feature in the part of the sky that also contains the constellation Centaurus. In this arm, gas, dust, and stars trace a curved lane around the galactic center, and the evolved yellow star that is the focus here sits within one segment of that lane. The presence of such a rare hypergiant in this setting reveals that this segment of the Centaurus arm has formed very massive stars in the relatively recent past, since stars of this mass live only a short time in galactic terms before they evolve into unstable expanded stages. The overall rotation of the Milky Way sets the background against which this environment develops. Stars and gas complete an orbit around the galactic center over many hundreds of millions of years, and during that time they drift in and out of the spiral pattern. The spiral arms themselves move through the disk at a pattern speed that is different from the orbital speed of individual stars. Because of this difference, a massive star forms where a cloud passes through the arm, then gradually moves away from the densest part of the pattern while it evolves. Nevertheless, during its relatively short lifetime, the hypergiant remains broadly associated with the same arm segment, and with the surrounding complex of gas and young stars that mark its origin. Observationally, the structure of the Milky Way is reconstructed from within, since the solar system also lies inside the disk. Astronomers map the distribution of gas using radio and millimeter wavelengths, follow the positions and motions of stars, and compare these data with models of spiral structure. Dust in the disk absorbs and scatters visible light, making some directions heavily obscured, but longer wavelength observations penetrate the dust and reveal where spiral arms cross the line of sight. In the direction of this evolved massive star, these studies identify a portion of the Centaurus arm at a distance of several thousand light-years containing clusters, ionized regions and bright massive stars. By measuring the brightness and spectra of the hypergiant and its neighbours, researchers place the system in this segment of the arm, rather than in a nearer or more distant structure, along the same line of sight. This placement anchors the star within the three-dimensional framework of the galactic disk. Within the Centaurus arm, the gas is organized into giant molecular complexes, filamentary clouds, and ionized cavities carved by previous generations of massive stars. The arm is not smooth. Instead, it consists of knots and lanes where star formation has proceeded at different rates. Some knots host very young clusters still partly wrapped in their birth material, while others contain more evolved groups of stars and large ionized bubbles. The hypergiant resides in one of these active knots, part of a wider complex that includes other luminous stars and extended nebulae. The exact boundaries of the complex are hard to define, but its overall scale spans many dozens of light-years large enough to hold multiple clusters and cloud fragments, yet still just one small patch of the arm. From the perspective of the wider galaxy, such a complex is one among many, but for this yellow hypergiant it forms the immediate large-scale setting. The radiation field in this sector of the arm is stronger than in quieter regions, because hot luminous stars pump out ultraviolet light that ionizes gas and heats dust. Stellar winds and past supernova explosions also shape the gas-creating cavities and shells that overlap and intersect. The star at the heart of this study contributes to this activity by emitting enormous amounts of light and by driving an outflow of gas from its extended atmosphere. The material it loses does not escape the galaxy. Instead, it joins the interstellar medium of the Centaurus arm, mixing with gas from other stars and from less massive objects. Over long periods, this enriched material can help to seed new generations of stars and planets. In this way, the position of HR 5171a within the Milky Way connects the life of a single yellow hypergiant to the broader cycle of gas dust and star formation that slowly reshapes the disk. Kinematic measurements show that the hypergiant moves with a velocity consistent with membership in the rotating disk, rather than in the halo or in a separate small system. Its radial motion combined with estimates of its distance supports its association with the Centaurus arm complex, rather than with nearer field stars. Neighbouring massive stars in the same part of the sky share similar motions, reinforcing the idea that they form a loose association born from the same general reservoir of gas. The details of the star forming history in this region are complex, but the presence of both very young objects and evolved unstable stars like this one indicates that star formation has continued for an extended period rather than any single brief burst. On the larger scales considered here, the hypergiant can be seen as one prominent member of a lively section of the Milky Way disk orbiting the galactic centre within the Centaurus arm and surrounded by the gas and stars that arise from the same spiral structure that once fostered its birth. In the part of the Milky Way where the constellation Centaurus lies, the disk of the galaxy is threaded by one of its major spiral arms. This arm is a broad lane of stars, gas and dust in which material gathers more densely than in the quieter regions between arms. Along its length, clumps and filaments of gas form giant complexes that host clusters, loose associations of young stars and large glowing nebulae. Within this structure, the segment that contains the yellow hypergiant connected with HR 5071A stands out as a crowded and active zone marked by the combined light of massive stars and by the imprint of their interaction with the interstellar medium. The arm itself curves around the galactic center at a distance of many thousands of light-years, and the star-forming segment near Centaurus is only one piece of this much longer pattern, yet it can be considered a self-contained environment for the study of the hypergiant and its neighbors. In this segment, gas is organized into giant molecular clouds that stretch over tens of light-years and into smaller clumps nested within them. These clouds are cold and dense enough for molecules to form and survive, and they represent the main reservoirs of star-forming material. Embedded in and around them are regions where recent star formation has already taken place. Here, hot luminous stars illuminate their surroundings and drive strong winds, creating bubbles and cavities in the surrounding gas. The result is a patchwork of cold, dark clouds, bright ionized volumes, and intermediate layers where radiation and material from different phases mix. The hypergiant sits within this patchwork, not at the very center of the arm as a whole, but in a local concentration where conditions have favored the birth of very massive stars. A star-forming complex in this context is a collection of clouds, clusters, and nebulae that share a common volume and a broadly similar motion through the galaxy. The complex around the hypergiant likely spans many dozens of light-years and contains a mix of stellar ages. Some stars in this complex are still very young, deeply embedded in their parental clouds, and best seen in infrared light. Others, including hot blue stars and more evolved objects, have already cleared away much of the surrounding gas. The yellow hypergiant is among the most evolved and unstable members of this population. Its presence alongside younger massive stars indicates that star formation in this complex has not occurred in a single brief burst, but has continued over an extended interval. That continuity allows different evolutionary stages of massive stars to coexist in the same general environment. The large-scale gas flows in the Centaurus arm help to sustain this activity. As the galaxy rotates, gas streams along the arm and into the gravitational potential wells of the giant clouds. Spiral density waves combined with local gravitational instabilities keep compressing and stretching the gas. In some regions, this compression raises the density high enough to trigger new collapses. In others, turbulence and pressure support prevent immediate star formation. The balance between these processes varies from place to place, so the arm displays a sequence of more and less active segments. The segment that includes the hypergiant shows clear evidence of enhanced activity, with multiple ionized and dusty regions signaling the effects of recent massive stars on their surroundings. Radiation from hot stars in the complex influences the temperature and ionization state of gas far beyond the immediate vicinity of each star. Ultraviolet photons travel through the lower density parts of the medium, ionizing hydrogen and other elements, and creating extended envelopes of warm gas. Where these photons encounter denser regions, they carve bright surfaces and can slowly erode the edges of clouds. Dust grains mixed into the gas absorb some of this radiation and re-radiate it in the infrared, producing glowing shells and arcs around clusters and around individual stars. The hypergiant contributes to this radiation field with its high luminosity, although its surface is cooler than that of the hottest blue stars in the complex. Its light still heats dust and gas in its proximity, and adds to the overall energy budget of the surrounding medium. Massive stars also influence the dynamics of the gas through their stellar winds. These outflows carry momentum that pushes on the interstellar medium, creating cavities and shells that can overlap and merge, Over time, this mechanical feedback can help to shape the structure of the star-forming complex, compressing some regions and dispersing others. Observations of the Centaurus arm segment around the hypergiant show arcs and bubbles consistent with this kind of interaction. Some of these structures likely result from the combined winds of many massive stars, while others may trace the influence of individual stars or small groups. The hypergiant joins this pattern with its own wind, which is expected to be dense and extended, although the details of its interaction with the ambient gas depend on local density and motion. Stars in the complex form loose associations as well as more tightly bound clusters. An association is a group of stars that share a common origin and motion, but are not strongly gravitationally bound over long timescales. In the Centaurus arm near this region, several such groups have been identified, containing hot blue stars, supergiants, and less massive companions. The yellow hypergiant is associated with one of these groupings, suggesting that it formed from the same broad reservoir of gas as its neighbours. Over time, the association expands and its members drift apart, but for now, they still trace a coherent structure that can be linked back to the parent clouds. This association provides a reference frame for interpreting the motion and properties of the hypergiant, since its shared velocity and location help anchor distance estimates and environmental conditions. The interstellar medium in this part of the arm is enriched by previous generations of stars. Supernova explosions and strong winds from older massive stars have already injected heavier elements into the gas, and these elements now form part of the dust and molecular content of the clouds. The composition of the gas influences how efficiently it cools and collapses, and affects the opacity and structure of the resulting stars. The hypergiant, as a descendant of this enriched material, carries in its atmosphere and deeper layers the chemical record of this prior history. At the same time, through its own mass loss, it returns newly processed material to the same environment, closing a local loop in the cycle of matter between stars and interstellar space. Not all aspects of the Centaurus arm environment around this star are known in equal detail. Distance estimates to different parts of the complex carry uncertainties, and overlapping clouds along the line of sight can complicate the interpretation of observations. However, taken together, maps of gas emission measurements of stellar motions and studies of cluster properties all support a coherent picture. The yellow hypergiant linked with HR 5171a resides in a busy star-forming segment of the Centaurus arm, surrounded by molecular clouds, young clusters and luminous massive stars. This segment stands as the immediate large-scale context between the galaxy-wide disk studied earlier and the more focused nebula structures that lie closer to the star. Within this environment, the next layer inward consists of the ionized and partially cleared cavities carved by the most energetic members of the complex, forming the transition from dense molecular material to the lower density regions that directly envelop the hypergiant and its nearest neighbors. The ionized region, known as GUM-48d, forms the next clear layer of environment around the star and its neighbors in the Centaurus arm. On large scales, this region appears as a wide, faint glow surrounding a more empty cavity, where gas has been heated and stripped of many of its electrons by the combined radiation of massive stars. An ionized volume of this kind, often called an H2 region, is a place where hydrogen atoms are repeatedly ionized by ultraviolet light, and then recombine, producing characteristic emission that makes the gas shine in specific colors. GUM-48d is an evolved member of this class. The brightest, hottest phase of its life as an ionized bubble lies in the past, yet the shell still marks a long history of interaction between luminous stars and the interstellar medium. Within this extended structure, the yellow hypergiant HR 5171a and a nearby blue star sit close to the projected center of the glow, linking the current configuration of the system to the formation and maintenance of the nebula. Inside a region like this, the gas temperature typically settles at several thousand degrees high enough that the motions of particles keep the gas relatively diffuse. Thermal pressure pushes outward, while gravity from the gas itself is too weak to confine the volume tightly. As a result, the ionized material expands into the colder, denser surroundings, sweeping up neutral gas into a slowly growing shell. Over a few million years, this process can enlarge the ionized cavity to many tens of light-years across. In GUM-48 observations show a ring-like appearance in some wavelengths, with brighter filaments outlining the edges and fainter emission filling the interior. This pattern matches the expectation for a shell that has expanded and thinned, so that most of the mass now lies near the boundary, while the inner parts remain warm but less dense. The star that is the focus of this study contributes a large flux of light, but its surface is cooler than that of the hottest early-type stars, so it does not dominate the hardest ultraviolet radiation. Instead, a nearby blue companion and other hot stars in the complex provide most of the ionizing photons that keep GUM-48d active. Together they maintain a balance between ionization and recombination that sets the current size and brightness of the region. The boundary between the ionized interior and the neutral exterior is not a sharp, unbroken shell. It is shaped by variations in the surrounding molecular clouds and by the motion of stars within the gas. In directions where the original cloud was less dense, the ionized gas has expanded farther, allowing the shell to bulge outward and even break open. In denser directions, the expansion has slowed, and the ionization front remains closer to the center. This uneven growth produces bright rims, arcs, and knots, where the ionized gas pushes directly against thick clumps of neutral material. Infrared maps reveal such structures as glowing bands and curved features, where dust at the edge of the cavity absorbs stellar light and re-radiates it at longer wavelengths. Around the hypergiant arc, like features seen in mid-infrared surveys, trace layers of dust that sit inside the larger GUM-48d shell, but still respond to the wider radiation field of the ionized region. Within the ionized volume, the gas is mostly hydrogen, with helium and heavier elements mixed in at lower abundance. These additional elements contribute emission lines in optical and infrared spectra that help to diagnose the conditions in the nebula. By studying the strengths and ratios of these lines, astronomers infer temperatures, densities, and ionization states in different parts of the region. GUM-48d appears as a relatively low surface brightness, extended nebula consistent with an older ionized bubble whose central stars have already evolved beyond their most extreme ultraviolet phase. The gas still maintains a roughly uniform temperature in the interior, but the overall density is modest, and the shell has expanded enough that the light is spread over a large area on the sky. This makes the nebula subtle in direct imaging but recognizable through careful mapping. The shape and size of the ionized region encode important information about the energy output and age of the central massive stars. Models of H2 region evolution show how an initially compact ionized sphere grows as hot stars switch on, expand the gas, and then gradually lose ionizing power as they evolve. In the case of GUM-48d, the presence of a yellow hypergiant at the center signals that at least one of the stars has moved into a cooler, more inflated stage, while the surrounding shell testifies to a past phase when the same system or its close companions emitted much stronger ultraviolet radiation. The current balance between gas temperature density and ionization level reflects both the remaining ultraviolet flux and the inertia of the previously heated material. At the outer edge of the ionized cavity, a thin transition layer forms where radiation chemistry and temperature change rapidly over a small distance. This zone, often described as a photodissociation region, contains neutral hydrogen partially ionized atoms and a variety of simple molecules. Dust grains in this layer absorb much of the incoming ultraviolet light and protect molecules in deeper regions from destruction. In GUM-48d, such layers appear as bright filaments and ridges, marking where radiation from the central stars interacts most strongly with the surviving molecular clouds. These boundaries are important because they regulate how far the ionized gas can expand and how efficiently the surrounding neutral material can cool, collapse, or be eroded. They also mark the places where material shed by the hypergiant or its neighbours first encounters the wider interstellar medium. Inside the cavity, the density is low enough that photons travel long distances between interactions. Light from the hypergiant and associated massive stars therefore permeates most of the interior, providing fairly uniform illumination, except where local dust concentrations cast shadows. The gas pressure remains higher inside the bubble than in the surrounding neutral medium, so the region continues to expand slowly, even as its central stars evolve. Recombination acts everywhere within the ionized volume, tending to return electrons to protons and to neutralize the gas, but the ultraviolet radiation field replenishes the ionization and sustains the luminous state of the nebula. In this way, GUM-48d remains a record of ongoing energy input from the massive stars at its core rather than a static shell. For the yellow hypergiant, this ionized region forms a broad, diffuse envelope that sits outside the more compact circumstellar structures directly created by its own wind and mass loss. The temperature, pressure, and density inside the H2 region set the outer boundary conditions into which the stellar wind flows. They influence how shocked gas cools, how dust survives, and how material lost by the star mixes into the interstellar medium. Before attention turns inward to the denser clouds and to the circumstellar matter lying much closer to the hypergiant GUM-48d, stands as the extended, softly glowing framework that surrounds the entire small group of massive stars of which this unstable yellow giant is a part. At the edge of the ionized cavity associated with GUM-48d, the environment changes from warm diffuse gas to cold, dense molecular material, and this transition marks the next layer in which the yellow hypergiant and its neighbours are embedded. A molecular cloud in this context is a region where hydrogen is largely bound into molecules and where temperatures fall to only a few tens of degrees above absolute zero, allowing gas and dust to clump together without being rapidly dispersed. In such conditions, the gas becomes opaque to much of the ultraviolet and visible radiation coming from nearby massive stars, and the dust grains within it absorb and scatter light in a way that shields the cloud interior. In images of the complex, these clouds appear as dark lanes cutting across the faint glow of the H2 region, or as bright cold structures in millimeter and infrared maps, where their dust and molecules emit weak but characteristic radiation. The pressure of the ionized gas pushes outward on these clouds, collecting them into arcs and ridges that trace parts of the expanding bubble and defining a textured boundary between the hot interior and the cooler surroundings. Within this crowded boundary zone, dense clumps form the birthplaces of new stars and preserve in their structure and composition the conditions that once give rise to the massive progenitor of the present hypergiant. The molecular material around the ionized cavity is organized into filaments and knots of many different sizes. Observations in spectral lines of carbon monoxide and other tracer molecules reveal multiple components along the line of sight, each with its own velocity indicating overlapping structures at slightly different positions in space. Within an individual filament, gravity, turbulence, and magnetic fields compete to set the balance between support and collapse. If the density remains low, turbulent motions and magnetic pressure can hold the structure up for long periods. If parts of the filament contract and their density crosses a critical threshold, they decouple from the surrounding flow and start to collapse more rapidly, forming dense cores. These cores are the immediate precursors of protostars. In the GUM-48D region, compact infrared sources and master emission associated with some clumps show that this process is ongoing, with deeply embedded young stellar objects already present in the same broad complex that also hosts evolved luminous stars. Dust mixed with the gas plays several important roles in this layer. Tiny solid grains absorb energetic photons from the central stars and from the wider star-forming complex, converting this energy into infrared radiation that escapes more easily. This process helps to regulate the temperature in the outer parts of the clouds, preventing them from heating up too much under the strong radiation field. Deeper inside, where the column of material is thicker, dust and molecules provide even stronger shielding, allowing temperatures to drop and molecules to survive for long times. The mixture of gas and dust also influences how the clouds cool during collapse, since radiative transitions in molecules and the thermal emission of dust allow the contracting material to lose energy and continue to sink inward. In regions closer to the cavity, the outer layers of the clouds are warmer and more eroded, while at larger distances the clouds retain thicker envelopes and a higher fraction of molecular gas. This gradual change in conditions across space creates a range of environments, from strongly irradiated cloud surfaces near the ionized gas to more secluded interiors farther away. Some parts of the molecular complex show clear morphological signs of interaction with the expanding ionized region. Pillar-like structures, bright rims, and curved fronts point back toward the center of the cavity, indicating that the pressure and radiation from the warm interior are sculpting the neutral material. Where a compression wave from the expanding H2 region encounters a pre-existing clump, it can increase the density and push the clump closer to gravitational instability, potentially encouraging the formation of new stars. In other cases, strong radiation and mechanical forces can erode lower density gas and disperse would-be star-forming clumps. In the zone surrounding the hypergiant, both behaviors appear to be present. Some clouds show signs of being partially ablated, while others harbor compact regions that are still shielded enough to sustain collapse. As a result, the molecular layer around the cavity contains a mix of very young stars collapsing cores and more diffuse gas that has yet to organize into dense structures. The chemical composition of these clouds reflects the history of prior star formation in the Centaurus arm. Heavy elements produced in older massive stars and spread by their winds and supernova explosions are now incorporated into the gas and dust of the molecular complexes. Measurements of elemental abundances and isotopic ratios indicate enrichment beyond primordial levels, consistent with several cycles of star formation and feedback in this part of the arm. These heavy elements contribute to the formation of dust grains, to the cooling efficiency of the gas, and to the variety of molecules found in the clouds, from simple diatomic species to more complex organic compounds. The presence of enriched material means that any new stars forming here, including lower mass stars and potential planetary systems, inherit a chemical mix shaped by previous generations. The hypergiant itself, as an evolved massive star formed from gas of similar composition, and now participates in the same cycle by returning processed material to the environment through its own mass loss. Kinematic studies of the molecular gas near the ionized cavity show that the clouds share a common range of velocities with the H2 region, reinforcing the conclusion that they belong to a single physically connected complex, rather than to unrelated foreground or background structures. Small differences in velocity from clump to clump trace internal motions such as infall expansion or shear, but the overall pattern ties the molecular layer, the ionized bubble, and the group of massive stars into one coherent three-dimensional configuration within the Centaurus arm. In this configuration, the molecular clouds occupy the cooler, denser side of the boundary, while the ionized gas fills the warmer interior, and the luminous stars, including the yellow hypergiant, lie near the interface, where their radiation and winds exert the strongest influence. Within the dark filaments and bright rims that constitute this molecular layer, star formation continues at a measured pace. Dense cores contract over hundreds of thousands of years, drawing in surrounding gas and forming new stars of various masses. Many will be of low or intermediate mass, long-lived and faint, compared with the hypergiant, while a smaller fraction will grow into new massive stars that can in time carve their own cavities and enrich the environment further. Complex molecules form on dust grain surfaces, and in the gas phase tracing the chemical richness of the region, but not greatly altering its large-scale dynamics. As this quiet but persistent activity precedes the molecular layer at the edge of GUM 48d, serves both as a shield that protects cold gas from intense radiation, and as a reservoir that supplies material for ongoing star formation in the same broad environment that now hosts the unstable luminous yellow star at its center. Within the evolved ionized bubble and the surrounding molecular layer, the next scale inward is defined by the group of luminous stars that share the same general volume and motion as the yellow hypergiant. This local population forms a loose association embedded in the Centaurus arm, where several massive stars, intermediate mass stars and fainter companions, occupy a region only a few tens of light-years across. Against the broader background of the arm, this association appears as a modest concentration rather than a very rich cluster, yet it contains objects of high luminosity that strongly influence the state of the nearby gas. Among them, the hypergiant stands out as one of the brightest and most evolved, while a neighboring blue supergiant and numerous less massive stars complete the immediate stellar setting. Together, these stars connect the large-scale gas structures of GUM 48d and its molecular clouds to the more compact system centered on the yellow star itself. One of the most prominent neighbors is a hot blue star located only a small angular distance away on the sky. This star has the spectral type of a B0 supergiant and is intrinsically very luminous, though still fainter in visible light than the yellow hypergiant, because much of its radiation emerges at shorter wavelengths. Its projected separation corresponds to many tens of thousands of astronomical units, a distance that places it well outside any tight binary orbit, yet still within the same general environment. Measurements of reddening radial motion and association with the ionized nebula indicate that the blue supergiant and the yellow hypergiant are likely at roughly the same distance and share the same large-scale complex, although some uncertainty remains about whether they form a bound pair or simply occupy the same region of the Centaurus arm. In either case, the blue star contributes significantly to the ultraviolet radiation that maintains the ionization of the surrounding gas and shapes the inner surface of the molecular shell. Beyond these two luminous objects, the association includes a population of other massive and intermediate mass stars. Some belong to small groups or clusters identified in infrared surveys, while others appear more dispersed. Their colors and spectra suggest a range of ages centered around a few million years in line with estimates for the age of the ionized region. The hotter younger members emit strong ultraviolet radiation and drive fast winds, while more evolved bright supergiants show broader lines and characteristic signatures of extended atmospheres. Many fainter stars likely of lower mass populate the same volume, though they are less conspicuous. Together, this collection of stars outlines a loose association rather than a compact gravitationally bound cluster. The common motion and location of its brighter members connect them to the same star-forming episode that once gave rise to the progenitor of the hypergiant. The spatial relation between the stellar association and the gas structures around it reflects a long history of interaction. The luminous stars, including the blue supergiant and the yellow hypergiant, lie near the center of the ionized cavity and close to the inner edge of the molecular clouds. Their radiation and winds have carved out much of the interior of GUM 48d, while the molecular filaments and clumps at the edge bear the imprint of long-term pressure and illumination. Observations show that the brightest parts of the ionized shell and some of the dense rims in the molecular layer are oriented with respect to the positions of these massive stars, consistent with the idea that they have been the main energy sources in the region over the lifetime of the bubble. The association as a whole thus acts as the engine that powers the evolved H2 region and maintains the contrast between the warm interior and the cooler surroundings. On smaller scales within the association, subtle gradients in stellar content and gas conditions appear. Regions closer to the center host the most luminous and evolved stars, including the hypergiant, the blue supergiant, and other bright objects, while areas slightly farther out show more embedded young sources still partially wrapped in their birth material. This arrangement suggests that the earliest, most massive stars formed near the densest part of the original cloud, where conditions allowed rapid growth, and that subsequent star formation has continued in nearby clumps influenced by feedback from the first generation. The presence of very young stars at the edges of the ionized cavity and more evolved massive stars near the center is consistent with ongoing spatially structured star formation across the complex rather than a single burst. In this pattern, the hypergiant represents a late evolutionary stage of the earliest massive population. Kinematic measurements provide further support for the association between the luminous stars and the surrounding gas. Radial velocities derived from stellar spectra and from emission lines in the ionized and molecular components fall within a common range, indicating that the stars and gas move together through the Centaurus arm. Small differences reflect internal motions and local gravitational effects, but there is no evidence for large discrepancies that would indicate unrelated foreground or background objects. This coherence in motion helps to place the association at a single distance and reinforces its identity as a physically connected group within the larger spiral arm structure. Within this framework, the yellow hypergiant is not an isolated luminous star, but part of a small network of massive objects sharing a common origin and environment. Some details of membership remain uncertain. The projected field includes stars at different distances along the line of sight, and disentangling which objects truly belong to the association requires careful analysis of distances, motions, and reddening. The nearby open cluster projected against the same general area of sky lies at a smaller distance, and is not part of the same physical group, even though it appears close in images. Similarly, fainter stars near the hypergiant may be unrelated field stars rather than genuine companions. Still, when consideration is limited to objects whose properties match the distance and extinction of the GUM 48d complex, a consistent picture emerges of a modest association centered on a handful of very luminous stars with the yellow hypergiant among the most conspicuous members. This picture is supported by multiple lines of evidence, but leaves room for refinement as new measurements improve distance estimates and stellar classifications. In terms of energy and mass flow, The association plays a central role in connecting the stellar and interstellar components of its environment. The combined radiation fields of the massive stars maintain the ionization of the cavity and heat the surrounding dust, while their winds supply momentum that shapes bubbles and arcs in the gas. Over time, material lost by the hypergiant and by other massive stars mixes into the inner parts of the molecular layer and into the more diffuse gas in the arm. This material carries heavy elements produced in the interiors of the stars and alters the composition of the interstellar medium from which future stars will form. On the timescales relevant for the association, this exchange is gradual, and the overall structure of the complex remains recognizable even as individual stars evolve. The local group of luminous stars with the yellow hypergiant near its center thus forms an intermediate scale between the global gas structures described earlier and the more compact circumstellar environment that surrounds the star itself. On scales smaller than the loose association of luminous stars in the Centaurus arm, the structure around the yellow hypergiant becomes that of a multiple system. The designation HR 5171 refers to a group of at least 2 and possibly more stars that share nearly the same line of sight and that are likely linked by their origin in the same star-forming complex. At the widest, clearly identified separation lies a hot blue star, while much closer to the hypergiant there are signs of additional structure that may include a compact companion or pronounced asymmetries in the extended atmosphere. Together, these elements form the immediate stellar architecture around the hypergiant setting, the stage for how its light and mass outflow interact with nearby space. At the largest scale within this system is the blue supergiant, often labelled as the B component. This star lies roughly 10 arcseconds away on the sky, which corresponds to a projected separation of tens of thousands of astronomical units if both stars sit at the same distance in the Centaurus arm. It is itself a very luminous object, with a surface temperature far higher than that of the yellow hypergiant, so that a large fraction of its energy output emerges in the ultraviolet. In visible light, it appears a few magnitudes fainter than the yellow star, partly because of its higher temperature, and partly because of interstellar and circumstellar dust that reddens the entire field. Measurements of its spectrum and motion suggest that it shares a similar distance and space velocity with the hypergiant, which supports the idea that the 2 stars belong to the same physical system rather than being a simple chance alignment. However, at such a large separation, the gravitational binding between the pair is relatively weak compared with the pull of the broader association and cloud complex, so there remains some uncertainty over whether they form a long-lived bound binary or a looser pair embedded in the same environment. Regardless of the exact binding status, the blue supergiant contributes strongly to the ultraviolet radiation field that fills the interior of GUM-48d, and helps to maintain the ionization of gas in the inner parts of the nebula. The light from this star, combined with that from the hypergiant and other massive neighbours, shapes the temperature and ionization state of gas and dust over many light years. Closer in on angular scales that require long baseline interferometry to resolve lies a more complex and less settled picture. Early interferometric observations of the hypergiant revealed a brightness distribution that could not be explained by a single circular disk. Instead, the resolved image showed a very large stellar disk surrounded by extended emission and marked by significant asymmetry. When these data were combined with a long photometric record showing periodic brightness variations, on a timescale of around 1,300 days, one interpretation was that the hypergiant forms a very close binary with the smaller companion. In this view, the primary and secondary stars share a common envelope of gas, orbiting within a single extended atmosphere that rotates approximately in step with their orbital motion. The companion in such a model would be significantly smaller than the hypergiant, perhaps 1/3 of its size, yet still a luminous star in its own right. The orbital period derived from the light curve would then correspond to the time required for the two components to complete one revolution inside their shared envelope. In this scenario, the deep and shallow minima in brightness would be due to mutual eclipses as one component passes in front of the other along the line of sight, while the overall asymmetry seen in interferometry would arise from the combined effect of two overlapping stellar disks and the thick surrounding gas. Such a configuration is often described as a contact or over-contact binary, meaning that both stars fill or overfill their critical gravitational surfaces so that mass can flow between them with little constraint, and both are embedded in the same gaseous envelope. For a very massive system, this phase represents an intense form of interaction in which orbital energy and angular momentum can be efficiently exchanged, with the envelope strongly affecting mass loss and rotation. In the case of this hypergiant, the initial interferometric and photometric analyses suggested that the system may be undergoing such an interaction, with the smaller companion orbiting deep within the extended atmosphere of the primary. Later observations and modelling have added nuance to this picture. Follow-up interferometry at multiple epochs again resolved a very large central disk and an extended shell of material, sometimes referred to as a molecular sphere, that contributes a sizable fraction of the near-infrared light. In some reconstructions, a secondary source appears near the limb of the primary disk, consistent with a close companion, but the exact brightness and location vary with time and with the details of the model used to fit the data. Studies of the light curve and spectrum have also emphasized that the hypergiant itself exhibits strong pulsations, surface changes and variations in effective temperature, all of which can produce brightness fluctuations and line profile changes independent of any eclipses. A more recent analysis has argued that the shape distortions seen in interferometric images and some components of the variability may be explained at least in part by the very low surface gravity of the swollen star and by non-radial pulsations, without requiring that the system be in a fully developed contact state. As a result, the status of the very close companion remains an open question. There is clear evidence that the central source is not a simple spherical star, and the additional structure, whether in the form of a genuine secondary star or of dense asymmetric regions in the envelope, lies very near the photosphere. At the same time, the specific picture of two stars in strict contact sharing a common envelope and producing strictly periodic eclipses is less secure than early models suggested. Some authors still consider a close binary to be a plausible interpretation, especially given the long-term periodic signal in the light curve, while others favour explanations that rely more heavily on pulsations and envelope structure. In this way, the system architecture on the smallest resolved scales around the hypergiant remains under active study. Even without a fully settled model, certain points are robust. The primary is extremely large, with a radius hundreds of times that of the Sun, and its outer layers are weakly bound by gravity. It is surrounded by an extended atmosphere or envelope that reaches beyond the region where the bulk of the visible light is formed. Within this extended region, localized enhancements in density and temperature can mimic the appearance of secondary components in interferometric data. At the same time, any genuine close companion would orbit within or just outside this envelope, so that its presence would naturally distort the shape of the primary and influence the local flow of gas. The combination of low surface gravity, strong pulsations, and possible tidal forces creates a highly structured environment in which the boundary between star envelope and companion is not sharply defined. On intermediate scales between the unresolved core and the wide blue supergiant, The hypergiant is also linked to shells and arcs of material that have been imaged in infrared light. Some of these structures appear centered on the yellow star and likely represent material lost through its wind in previous episodes. Others may trace combined effects of the local group of massive stars. At the level of system architecture, these shells form part of the gravitational and radiative environment experienced by any close companions, and they carry the imprint of how the star and possibly its companions have interacted with the surrounding gas over time. They do not yet belong to the detailed circumstellar envelope that lies directly above the photosphere, but they mark the outer bounds of the immediate system in which orbital motions, mass loss, and radiation from the hypergiant and its nearest neighbours are closely linked. In summary, the current understanding places HR 5171a within a small multiple system that almost certainly includes a wide hot blue star and very likely includes additional structure or companions at much smaller separations. The wide component helps to define the ionized nebula and the shared motion of the system through the Centaurus arm, while the unresolved or barely resolved inner architecture controls how the hypergiant exchanges mass and momentum with its closest surroundings. This layered system, ranging from the wide blue supergiant down to possible companions orbiting within the extended atmosphere, forms the immediate outer framework for the more detailed circumstellar nebula and stellar wind that surround the yellow hypergiant on still smaller scales. Yellow hypergiants form a very small and unusual class of stars, and the bright object at the center of this environment is one of them. A yellow hypergiant is defined by its extreme luminosity, its very large radius, and its unstable swollen atmosphere. On a temperature-luminosity diagram, these stars occupy a region above the ordinary supergiants, at luminosities of several 100,000 to around 1 million times that of the Sun, and at surface temperatures between roughly 4,000 and 8,000 degrees. They sit between the cooler red supergiants and the hotter blue supergiants, yet they are not simply intermediate in every respect. Instead, they mark a brief and unstable stage in the life of very massive stars where radiation pressure in their extended envelopes comes close to balancing gravity, and small changes in internal structure can produce large responses at the surface. The hypergiant in Centaurus follows this pattern. It radiates so much energy that its outer layers are weakly bound, and its measured size at hundreds to perhaps around 1,000 times the radius of the Sun places it among the larger stars known. Even at a moderate effective temperature compared with the hottest blue stars, its enormous surface area allows it to shine with a power that places it near the top of the diagram, where only the most massive and luminous stars appear. In physical terms, the defining property of a yellow hypergiant is its high ratio of luminosity to mass. Radiation leaving the interior exerts an outward force on the gas in the envelope, while gravity pulls inward. When the luminosity approaches a critical value known in theory as the Eddington limit, the outward push from photons becomes comparable to the inward pull of gravity in some layers. In such a situation, the outer envelope becomes marginally stable, and even modest disturbances can drive matter outward in strong winds or episodic outflows. The atmospheres of yellow hypergiants therefore show signatures of heavy mass loss, such as broad and often asymmetric spectral lines formed in extended gas and infrared excesses produced by dust that condenses in expelled material. The star in this study fits this picture with a dense outflow that carries material away at speeds of tens of kilometers per second and builds up a circumstellar environment that is much more massive and structured than that of an ordinary supergiant. The rarity of this class reflects the short time that very massive stars spend in such a state. In the Milky Way, only about a dozen convincing examples of yellow hypergiants are known, even though hundreds of millions of stars populate the disk. This scarcity is not due to observational difficulty alone, since these stars are intrinsically very bright, but rather to the combination of their brief lifetimes and the specific mass range and evolutionary paths required to reach this stage. A star must be massive enough to achieve very high luminosity, yet must also evolve through a region of moderate surface temperature where its envelope expands dramatically. Models of massive star evolution suggest that only certain initial masses and rotational properties pass through this region in a way that produces a yellow hypergiant phase, and even then the duration of that phase is expected to span only a small fraction of the total lifetime. The presence of such a star at the centre of the GUM-48d complex therefore indicates that the local star-forming history has produced at least one very massive object, and that it is currently caught in a comparatively brief unstable interval of its evolution. Compared with red supergiants, which have cooler surfaces and even larger radii but somewhat lower average surface gravity, yellow hypergiants occupy a region where temperatures are higher and ionization in the atmosphere is greater. This affects the opacity of the gas and the way radiation flows through the envelope. In particular, changes in ionization with temperature can cause abrupt shifts in opacity, which in turn feed back on the local balance between radiation pressure and gravity. These feedbacks are thought to contribute to the instability of the yellow hypergiant regime. Observationally, such stars display strong variability in brightness and spectrum on timescales, from months to years, as the atmosphere responds to changes in internal structure and to pulsations. The star in Centaurus shows this behavior with recorded fluctuations in light and spectral features that indicate changes in effective temperature radius and wind properties over time. These variations do not follow the simple regular pattern seen in some pulsating stars, but instead reflect a combination of pulsation, atmospheric turbulence, and mass loss, typical of this very luminous, marginally stable state. When considered as a group, yellow hypergiants share several observable traits beyond their position on the temperature-luminosity diagram. Their spectra often show strong emission and absorption features from hydrogen metals and molecules formed in extended stratified atmospheres and winds. Many display infrared excess, revealing warm dust in their immediate surroundings. Some show evidence of past eruptions or enhanced mass loss events that have produced shells or arcs of material at varying distances from the star. The object associated with HR 5171 follows this pattern in several respects. It has a complex spectrum with features tracing both photospheric layers and outflowing gas, and it is surrounded by circumstellar dust that glows in the infrared. Interferometric observations confirm that its apparent disk is much larger than that of a normal supergiant at similar distance and brightness, and that the emission extends beyond the region where the bulk of the visible light is formed. These findings are all consistent with classification as a yellow hypergiant. Despite these commonalities, individual members of the class can differ in detail. Some are cooler and nearer to the red supergiant domain. Others are hotter and closer to the realm of luminous blue variables and blue supergiants. Their masses' rotation rates and histories of mass loss can vary, leading to differences in behavior. In some cases, stars appear to move back and forth in effective temperature within a certain range, possibly crossing a region, sometimes described as the yellow evolutionary void, where stability is particularly hard to maintain. The star in Centaurus appears to occupy a part of this general area, and shows evidence of significant changes in effective temperature over decades, as derived from its spectra and light curve. However, the precise evolutionary track that has brought it to its present state remains subject to modelling uncertainties, and some of its detailed properties, such as its current mass and the exact structure of its envelope, are still constrained only within ranges rather than by single values. There is also ongoing discussion about how best to define the boundaries of the yellow hypergiant class. Some authors emphasize luminosity thresholds, others focus on spectroscopic features and evidence of instability, and still others stress the presence of dense winds and circumstellar material. In practice, classification often relies on a combination of these criteria. For the star at the center of GUM-48d, the combination of very high luminosity intermediate surface temperature, large radius, strong mass loss, and marked variability makes its status as a yellow hypergiant robust, even though the finer details of its internal structure and future evolution remain under study. New observations and models may refine estimates of its current mass radius and temperature, but they are unlikely to remove it from this rare group. In the wider stellar population of the Milky Way, yellow hypergiants are usually found in or near regions of recent massive star formation, often associated with clusters and associations containing hot blue stars and evolved supergiants. The environment described in earlier sections fits this pattern, with the hypergiant embedded in a star-forming complex that also hosts a blue supergiant and other luminous neighbours. This context helps to confirm its nature and to provide constraints on its age and initial mass, since these can be estimated by comparing its properties with those of other stars in the same association and with theoretical isochrones. Even without assigning precise numbers, the general features of the environment and the star's brightness place it firmly among the upper mass range of stars in its group. As the narrative moves inward from the classification of yellow hypergiants as a rare class toward the specific surroundings of this star, the next layer consists of the extended circumstellar nebula and large-scale wind that this kind of object naturally produces. The high luminosity and marginal stability of the swollen envelope ensure that mass loss is a central feature of the yellow hypergiant state, and the material carried away in this flow builds a structured environment around the star on scales larger than the photosphere but smaller than the wider ionized cavity of GUM-48d. This circumstellar region formed directly by the star's outflow represents the next inward step in understanding how the properties of a yellow hypergiant manifest themselves in space. Between the wider association of massive stars and the immediate stellar atmosphere lies a zone of circumstellar material built directly from the mass lost by the yellow hypergiant. This region forms a nebula on scales much larger than the star itself, yet still far smaller than the broad shell of GUM-48d. It consists of gas and dust expelled in a dense stellar wind, and impossible episodes of enhanced outflow now arranged into shells, arcs and diffuse clouds that extend outward in all directions, though not with perfect symmetry. The circumstellar nebula acts as an intermediate buffer between the star and the surrounding interstellar medium, mediating how light momentum and processed material from the hypergiant enter the larger environment. In images at infrared wavelengths where warm dust glows most clearly, the space around HR 5171a does not appear empty. Instead, extended emission surrounds the point like central source, fading gradually into the background of the wider complex. In some datasets, this emission resolves into arc-like features that curve around the star at distances many times greater than the size of the stellar disk. These arcs and shells likely trace episodes in which the rate of mass loss changed, or the geometry of the outflow shifted, leaving behind compressed layers of dust and gas that now radiate in response to the strong stellar light. In other directions, the nebula appears more diffuse, suggesting that the wind has flowed more freely, or that interaction with the ambient gas has smoothed out earlier structure. The overall picture is that of a circumstellar envelope that is extended clumpy and shaped by both the internal variability of the star and the external pressure of the surrounding medium. The outflow that builds this nebula originates in the upper layers of the hypergiant atmosphere, where radiation pressure and pulsations push material beyond the point where gravity can pull it back. Once gas crosses this escape threshold, it accelerates outward into a stellar wind that carries mass away from the star at speeds of tens of kilometers per second. Close to the star, the density in this wind is high, and collisions between particles are frequent. As the wind travels farther, it expands and thins, but the total mass carried outward over time is substantial. For a yellow hypergiant, the rate of mass loss can exceed that of a typical supergiant by a significant factor, so that over the duration of this unstable phase, a non-negligible fraction of the remaining envelope is shed. The gas in the wind contains ions, atoms and molecules, and dust grains condense in cooler zones as the material expands and cools. These grains then absorb optical and ultraviolet light from the star and re-radiate it in the infrared, making the structure of the circumstellar nebula accessible to telescopes that operate at those wavelengths. The geometry of the nebula reflects more than a simple steady wind. Variations in mass loss rate, perhaps linked to pulsations or changes in the internal structure of the envelope, can create denser shells embedded in a more continuous flow. If the star undergoes an episode of especially strong outflow, the material expelled during that time may pile up at a particular distance before merging with the rest of the wind, producing an arc or ring. Over time, the outward motion of these features moves them into the larger environment where they can interact with the general gas of the GUM-48D region. Differences in density or pressure in the external medium can also distort the shape of the nebula. If the star and its surrounding gas move slightly with respect to the ambient material, the wind may encounter higher pressure on one side than on the other, leading to compressed structures that resemble a bow shape or a bright arc facing the direction of motion. The observed arcs around HR 5171A are consistent with such a combination of internal and external shaping effects, though the exact contribution of each remains the subject of detailed modelling. Within the circumstellar, nebula conditions vary strongly with distance from the star. In the inner parts, the gas is warmer and more ionized, and the radiation field is intense. Closer to the outer edge, temperatures drop. Molecules become more stable, and dust grains survive for longer periods. Spectroscopic observations of the region reveal emission and absorption from molecules such as carbon monoxide and from various metal lines, indicating a layered structure in which different species dominate at different radii. These layers trace the gradual cooling and dilution of the outflow as it moves outward. Because the wind density falls roughly with the square of the distance from the star under steady conditions, inner regions respond quickly to changes in mass loss, while outer zones preserve a record of behavior integrated over longer times. By comparing emission from material at different distances, astronomers infer that the hypergiant has not lost mass at a perfectly constant rate, but has instead experienced phases of stronger and weaker outflow. The nebula thus functions as a time-structured record of the star's recent history, written into space in the distribution of gas and dust. The mass contained in the circumstellar envelope is not precisely known, but estimates suggest that it may amount to several solar masses accumulated over many thousands of years. This material is not yet part of the general interstellar medium, because it still resides in the gravitational and radiative influence of the star, but it is no longer bound tightly enough to be reabsorbed into the stellar envelope. In terms of chemical composition, the outflow carries both material that retains the initial composition of the outer layers and gas that has been enriched in elements produced in deeper nuclear burning zones and then mixed outward. As a result, the circumstellar nebula contains higher concentrations of certain elements, such as nitrogen relative to the ambient medium, and these enhancements can be detected in spectral lines. Dust grains in the nebula may also show signatures of this enrichment in their mineral makeup. Over time, as the wind-driven shell interacts with the broader environment, this processed material will mix into the surrounding gas, but for now it remains concentrated in the zone around the hypergiant. The interaction between the stellar wind and the wider environment further shapes the outer parts of the circumstellar nebula. Where the freely expanding wind encounters the pressure of the ionized gas filling gum, 48D a boundary layer forms in which the wind slows and piles up. This layer can take the form of a termination shock, where the kinetic energy of the wind is converted into heat, and a contact region where the shocked wind meets the external medium. Structures seen as arcs in infrared images may coincide with such zones of interaction, especially if the ambient density is higher in certain directions. If denser clumps of molecular gas lie nearby, the wind can wrap around them, producing asymmetric shapes. The resulting pattern of shells and arcs encodes information about both the properties of the wind and the distribution of external gas. Although uncertainties in distance and projection limit the precision of such inferences, the general conclusion that the circumstellar nebula is shaped by both the star and its environment is robust. On sky images, the circumstellar emission merges gradually into the broader glow of the GUM-48D complex, so that there is no single sharp boundary between material that is primarily star-made and material that belongs to the wider nebula. Instead, there is a continuous transition in which the density and chemical signature of the gas and dust change with radius. Closer in, the influence of the hypergiant dominates, and the material clearly reflects its mass loss. Farther out, the composition and kinematics become more similar to those of the general ionized and molecular medium. In this sense, the circumstellar nebula acts as both a distinct structure and a bridge carrying matter from the stellar envelope into the surrounding region. It moderates how quickly the star wind and radiation couple to the environment, and provides a setting in which dust can form, survive for some time, and then eventually disperse. From the perspective of the layered description followed here, the large-scale circumstellar nebula around HR 5171a represents the first zone that is directly and entirely produced by the star itself, rather than by the combined action of many stars in the complex. It surrounds the system on scales of many thousands of astronomical units, extending far beyond the photosphere, but still lying well inside the main shell of the H2 region. Within this zone, the next step inward leads to the bound outer envelope and inflated atmosphere of the hypergiant, where the stellar wind is launched, and where the physical conditions responsible for the high mass loss rate are set in detail. Just beyond the swollen outer envelope of the yellow hypergiant, the gas that fails to remain bound transitions smoothly into a steady outflow, and this is the region where the stellar wind and mass loss flow take shape. Here, radiation escaping from the bright interior and motions within the extended atmosphere combine to push material outward. The result is a slow but dense wind that carries gas and dust away from the star and fills the inner parts of the circumstellar nebula described earlier. In this zone, the flow is still dominated by the gravity and radiation of the hypergiant, rather than by the conditions in the wider GUM-48D complex, so its properties reflect the star's own structure and variability more directly than they reflect the larger environment. The wind begins in the layers just above the visible surface, where the gas is partially ionized and where the effective gravity is already low because of the high luminosity. In these layers, photons exert an outward push on atoms, ions, and small dust grains. When the luminosity is high enough, this radiative acceleration can exceed the local pull of gravity, especially in regions where the opacity is enhanced by spectral lines or by dust. Pulsations in the envelope, which cause the surface to move in and out on timescales of months to years, further assist the process by lifting material to greater heights where it can be more easily accelerated. Once gas reaches a point where the net force directs it outward, it no longer falls back. It joins the flow and accelerates into the wind-trading gravitational potential energy for kinetic energy as it moves away from the star. The velocities reached in this wind are modest compared with those of very hot compact stars, but they're still significant. Estimates for the hypergiant's outflow indicate speeds of a few tens of kilometers per second, enough to carry material to great distances over thousands of years. Because the mass loss rate is high, the density in the inner wind is large and collisions between particles are frequent. This high density makes the wind optically thick in some directions and at some wavelengths, especially close to the star, so that the transition from the bound atmosphere to the free outflow is gradual rather than sharp. In this inner region, the gas is warm and ionized, and the radiation field is intense, so that the ionization state and temperature adjust continuously as material flows outward. Observationally, the wind region reveals itself in the shapes of spectral lines formed in the circumstellar gas. Profiles of strong lines, such as hydrogen-Balmer lines, often show a characteristic combination of emission and absorption that indicates outflow. Part of the line forms in gas moving toward the observer and absorbs photons from the star, producing a blue-shifted absorption component, while other parts form in gas moving in different directions and re-emit light, giving rise to a broad emission feature. Together, these components create what is known as a P Cygni profile, a hallmark of expanding envelopes. In the hypergiant associated with HR 5171, such profiles have been recorded with broad emission wings and asymmetries that trace the velocity field and density distribution in the wind. Additional information comes from infrared and radio measurements of free emission, which arises when electrons scatter off ions in the ionized gas, and from molecular lines that form farther out where the gas has cooled. These diagnostics together indicate a wind that is dense, extended, and structured, with significant mass loss continuing over long periods. One key quantity in understanding the wind is the mass loss rate, the amount of mass carried away per unit time. Estimates for this hypergiant vary, reflecting uncertainties in the clumping of the gas, the geometry of the flow, and the distance, but they consistently indicate values far above those typical for ordinary supergiants. Even within the range of plausible numbers, the cumulative effect over the duration of the yellow hypergiant phase is substantial. Over tens of thousands of years, the star can lose several solar masses of material through its wind. This loss reshapes. The envelope reduces the mass available for later burning stages and builds up the circumstellar nebula. Yet the precise rate at any given moment is not constant. Long-term monitoring shows that line strengths and profiles change with time, implying that the wind density and velocity structure vary on timescales from months to years. Some of these changes may track pulsation cycles, while others reflect more irregular behavior in the unstable envelope. The structure of the wind is not perfectly smooth. Instabilities in the acceleration process, such as those linked to line driving, can cause small perturbations in density to grow as the gas flows outward, leading to clumps and rarefied regions. Large convective cells at the surface and non-radial pulsations can also inject asymmetries into the base of the flow. As a result, the wind becomes clumpy and anisotropic, with some directions carrying more mass than others at a given moment. This clumping affects how spectral lines form and how emission at different wavelengths is interpreted, since a clumped wind can produce the same observed emission with a lower total mass loss rate than a perfectly smooth one. It also shapes how dust forms, because dust grains condense more efficiently in denser pockets, where gas can cool and where molecules can aggregate on grain surfaces. Over time, these inhomogeneities imprint themselves on the circumstellar nebula, contributing to the arcs and irregular structures seen in infrared images at larger radii. As the outflow moves away from the star, it gradually transitions from a zone where the velocity is still increasing to a region where it reaches an approximately constant terminal value. The acceleration region typically spans several stellar radii, within which the balance between radiation pressure, gravity, and gas pressure determines the velocity gradient. Beyond this zone, the gas coasts outward at nearly constant speed, and the density profile follows a decline that depends mainly on the mass loss rate and wind velocity. In the case of this hypergiant, the extended atmosphere and low surface gravis mean that the acceleration region is likely more extended and complex than in more compact stars, with overlapping effects from pulsations, shocks, and changing ionization. Observational constraints on the detailed velocity law remain limited, but the general pattern of a slow, dense wind is well established. In addition to the continuous outflow, there are indications that the star may have experienced episodic phases of enhanced mass loss. Evidence for such phases comes from the presence of multiple shells or arcs at different distances in the circumstellar nebula, and from long-term changes in spectral features that suggest intervals of stronger wind followed by quieter periods. However, the exact timing and magnitude of these episodes are not yet firmly established, and interpretations must account for the blending of signatures from continuous and episodic mass loss. What is clear is that the outflow has not been perfectly steady over the star's recent history, and that variations in the wind have left spatially separated traces in the surrounding gas and dust. The wind region also forms the interface between the star and any very close companions or envelope structures discussed earlier at the system level. If a compact companion or denser symmetric region lies within or just above the extended atmosphere, it can locally enhance or redirect the flow. Tidal forces, orbital motion, or local heating can create preferred channels for the outflow, leading to anisotropic mass loss. In such cases, certain directions may show higher densities or different velocities compared with a purely spherical wind. Interferometric imaging of the inner environment of the hypergiant indeed suggests departures from perfect symmetry, although the degree to which these are due to companions, pulsations, or both remains under investigation. Regardless of the exact cause, the effect on the wind is to introduce directional structure close to the star that later expands outward and contributes to the complex shapes seen in the circumstellar nebula. As the wind continues outward, it eventually reaches the distances where it encounters the pressure of the ionized gas and molecular material in the wider environment. There, its free expansion slows, shocks can form, and the flow becomes part of the broader circumstellar and interstellar medium. Within the layer considered in this section, however, the gas remains dominated by the forces and conditions imposed by the hypergiant itself. This inner wind region, extending from just above the bound outer envelope to the radii where the flow becomes part of the larger nebula, is where the crucial process of mass removal from the star takes place. It controls how quickly the envelope is depleted, how the circumstellar material is supplied, and how the star exchanges momentum and chemical products with its immediate surroundings. From here, the description of the system can move inward to the inflated outer envelope and extended atmosphere that feed this dense, slow wind, and that define the boundary between the stellar interior and the outflowing gas. The inflated outer envelope of the yellow hypergiant forms a broad, diffuse layer of gas that remains gravitationally bound to the star while already showing signs of the marginal stability that characterizes this phase. It lies inside the region where the wind flows freely into space, and outside the deeper layers where density and pressure rise steeply. In this zone, the gas is extended over many stellar radii and held in a delicate balance between the inward pull of gravity and the outward forces from radiation gas pressure and pulsation. For HR 5171a, this envelope is the part of the star that occupies most of its apparent volume, so that when interferometric observations measure a very large size, they are largely measuring the extent of this low-density inflated layer, rather than a sharp, well-defined surface. The temperature in the outer envelope decreases gradually with increasing radius. At the inner edge of this region, the gas is still hot enough that hydrogen and helium are mostly ionized, and radiation diffuses outward through a mixture of free electrons and ions. Farther out, as density falls and the gas expands, ionization fractions change and recombination becomes more significant. These changes in ionization affect the opacity of the gas because different ions and neutral atoms absorb and scatter photons in different ways. In certain temperature ranges, small changes in temperature and density can produce large changes in opacity, which in turn alter how efficiently radiation pushes outward. This sensitivity contributes to the difficulty of maintaining a smooth, steady structure in the envelope. The result is an extended region where the local balance between radiation pressure and gravity varies with depth in a complex way rather than following a simple monotonic profile. The gravitational acceleration in this outer envelope is low because the stellar mass is concentrated at smaller radii, while the gas here lies far from the center. At the same time, the luminosity of HR 5171a is extremely high, so that the ratio of radiative force to gravity expressed in theory through the Eddington parameter approaches unity in some layers. Where this ratio comes close to 1, the effective gravity felt by the gas is very weak. In such zones, even modest perturbations such as those produced by pulsations or local convection can send material outward or inward over large distances. Hydrostatic equilibrium, the standard approximated balance in ordinary stellar envelopes, becomes fragile and can be broken locally, leading to motions that propagate through the envelope. This is one reason why the star shows large amplitude variability, and why its atmosphere does not resemble that of a stable compact object. Energy transport in the inflated envelope proceeds through a combination of radiation and convection. In deeper layers, radiation carries most of the energy outward, with photons scattering many times as they diffuse through the dense gas. As one moves outward and opacity changes, convection can become more important, especially in regions where partial ionization increases the heat capacity of the gas and makes it easier for rising parcels to carry energy efficiently. In these convective zones, large cells of gas rise and fall on timescales set by the local sound speed and scale height. For a star as extended as this hypergiant, the convective cells near the outer envelope are expected to be very large, covering a significant fraction of the visible hemisphere. Even though the detailed surface patterns belong to a slightly deeper layer, the convective motions originate and develop through this inflated region, shaping its density and velocity structure. These motions introduce irregularities in temperature and density that then feed back into the local radiative acceleration and the onset of the stellar wind. The density profile across the outer envelope declines with radius, but more slowly than in a simple compact star because of the inflation. In a standard supergiant density, drops steeply over just a few scale heights near the surface. In a yellow hypergiant like HR 5171, a low effective gravity and high radiation pressure stretch this region so that gas of intermediate density occupies a much larger radial extent. This extended profile means that the transition from the inner stellar layers to the wind is drawn out over many stellar radii. Within this extended transition zone, the speed of sound, the escape speed, and the local radiative acceleration all change gradually rather than abruptly, and the sonic point where the outflow passes from subsonic to supersonic speeds can lie relatively far from the depth where most of the continuum light is formed. The inflated envelope therefore acts as both part of the star and as part of the launch zone for the wind. Chemical composition in the outer envelope reflects both the initial makeup of the star and the internal processing that has already occurred. Convection and other mixing processes have likely brought material from regions where hydrogen burning has converted some hydrogen into helium and nitrogen, up into layers that now reside in the envelope. As a result, the gas here is expected to show enhanced nitrogen and altered ratios of carbon and oxygen compared with the original composition of the surrounding interstellar medium. Observations of spectral lines formed in the extended atmosphere support this picture with abundance patterns consistent with material that has experienced partial nuclear processing. These abundance changes do not strongly alter the large-scale dynamics of the envelope, but they do affect opacities in some wavelength ranges and provide important clues to the prior evolution of HR 5171A. They also mean that the gas leaving the envelope to join the wind carries with it a chemical fingerprint of the star interior. Turbulent motions are pervasive throughout the inflated region. In addition to organized convective flows, there are random small-scale velocity fields driven by the interplay of convection radiative forces and pulsations. These motions broaden spectral lines beyond what would be expected from thermal motion, alone a phenomenon often described as macroturbulence when measured in photospheric lines. In the outer envelope, similar motions introduce irregularities in density that make the medium clumpy rather than perfectly smooth. This clumpiness affects how radiation is transported because photons can escape more easily through low-density channels, while being trapped longer in denser pockets. It also influences where dust can form, since dust grains condense more readily in regions where gas can remain cool and dense for sufficient time. Over long periods, these inhomogeneities help seed the larger scale structures that appear farther out in the wind and circumstellar nebula. The inflated envelope also hosts pulsations that move the outer layers in and out on timescales from months to several years. These pulsations are global oscillations driven by changes in opacity and energy flow in partial ionization zones. When a layer of gas is compressed, its temperature and ionization change, modifying the local opacity and thus the radiative force. Under conditions present in yellow hypergiants, this can lead to cycles in which compression increases opacity and traps heat, causing the layer to rebound, expand, and then cool, which in turn reduces opacity and allows radiation to escape. The result is a repeating pattern in which layers move radially while exchanging energy with the radiation field. In the outer envelope of HR 5171, such pulsations can reach amplitudes large enough to significantly change local density and radius over each cycle. These radial motions directly influence the base of the wind because they periodically lift gas to heights where it can be more readily accelerated outward. The boundary between the inflated envelope and the freely flowing wind is not a rigid surface. Instead, it is a region where the local conditions gradually shift from those that support bound gas to those that allow continuous escape. Inward of this boundary, the gas trajectory can still involve rising and falling, with some material returning inward after a partial excursion. Outward of it, the trajectory becomes monotonic, with gas moving away and never returning. The position of this effective boundary depends on the mass loss rate, the luminosity, and the current state of pulsation and convection. In periods of stronger mass loss, the transition region moves inward, and more of the envelope participates in the outflow. In quieter periods, the boundary moves outward, and a larger fraction of the outer layers remains bound for longer times. This dynamic boundary underscores the idea that the inflated envelope is not a static structure, but a dynamically active layer linking the deep interior to the external wind. In terms of observable properties, the inflated envelope contributes to the apparent size and brightness distribution of the star. Interferometric measurements sensitive to different wavelengths see the star as larger or smaller, depending on which depth they probe, because different wavelengths emerge from different optical depths within the extended atmosphere. In bands where molecular opacity is high, or where dust close to the star emits strongly, the apparent radius can increase, reflecting the contribution of outer layers. This wavelength dependence is a direct signature of the extended stratified nature of the envelope. It also means that defining a single sharp radius for HR 5171A is somewhat artificial, since the transition from optically thick to optically thin gas occurs over a finite radial range rather than at a thin shell. Within the framework of the layered description followed here, the inflated outer envelope of the hypergiant is the last region in which gas remains mostly bound, while still being strongly affected by the proximity to the radiative stability limit. It encompasses the partial ionization zones, convective motions, pulsations, and turbulence that together prepare material for escape. Outside this region, the gas behaves more like a classical stellar wind. Inside it, the gas becomes part of the deeper atmosphere and photospheric layers, where most of the observable continuum light is formed and where the emergent spectrum and surface patterns of HR 5171A take shape. In this sense, the extended envelope is both a structural component of the star and a transition zone that channels energy and matter from the interior into the surrounding space. In the layered structure of the yellow hypergiant, the photosphere is the thin region where most of the visible light escapes into space, and it marks the apparent surface that telescopes effectively see. In a simple compact star, this layer sits just above the dense interior and has a relatively sharp location, but in a star as inflated as HR 5171A, the photosphere is spread across a broad, low-density envelope. Instead of a single, well-defined surface, there is a finite region in which the gas changes from being opaque to transparent over a range of depths. Different wavelengths form at slightly different levels so that the apparent radius of the star depends on the color at which it is observed. When interferometric measurements report a very large size for the hypergiant, what they resolve is essentially the radius at which the continuum in a given band becomes optically thin, rather than a rigid physical boundary. The concept of effective temperature helps to describe this extended surface in simple terms. Effective temperature is defined as the uniform temperature that a blackbody sphere of the same radius would need in order to radiate the same total power. For this star, spectral classification and modeling of its energy distribution indicate a temperature in the range typical of late yellow or early cool supergiants, around a few thousand to several thousand degrees above absolute zero. This is much cooler than the temperature of hot blue stars, but warmer than that of red supergiants. Despite this moderate surface temperature, the enormous radius of the hypergiant means that the total amount of energy radiated per second is extremely high, of the order of several 100,000 to around 1,000,000 times the luminosity of the Sun. The photosphere therefore shines as a very bright yellowish to orange source when corrected for the effects of interstellar dust. The observed colour of the star, however, is not determined by the photospheric temperature alone. Dust in the interstellar medium and in the circumstellar envelope absorbs and scatters blue light more strongly than red light, a process known as reddening. As a result, the direct light from the photosphere arrives at Earth with its blue component reduced, making the star appear redder and slightly fainter than it would in a dust-free environment. By comparing the observed colours and spectrum with theoretical models of stellar atmospheres, astronomers estimate the intrinsic temperature and brightness of the photosphere and the amount of reddening along the line of sight. For HR 5171, these analyses show significant extinction consistent with its location in a dusty star-forming complex and with its own contribution of circumstellar dust. Correcting for this extinction yields an intrinsic colour and temperature that place the photosphere in the yellow hypergiant regime. The spectrum of the star encodes detailed information about conditions in the photosphere and immediate surroundings. Spectral lines from neutral and singly ionized metals such as iron and calcium appear prominently as expected for a cool luminous supergiant. The strengths and widths of these lines, along with their relative depths, allow estimates of effective temperature, surface gravity, and chemical abundances in the photospheric layers. The low surface gravity inferred from the line shapes reflects the huge radius and high luminosity of the star, distinguishing it clearly from less evolved giants, and even from ordinary bright supergiants. In addition to absorption, features some lines show emission or complex profiles influenced by the extended atmosphere and wind, but the underlying photospheric component remains visible and provides a baseline against which these circumstellar effects are interpreted. Because the photosphere spans such a large volume and is connected to an inflated envelope, the physical conditions within it are not perfectly uniform. Temperature density and velocity vary with location on the surface and with depth, and these variations evolve with time. From a distance, these inhomogeneities average into a single effective set of parameters, but careful monitoring of spectra and brightness reveals that the photosphere of the hypergiant is not static. Over years and decades, the star shows changes in colour and temperature inferred from its spectrum, with episodes in which it appears slightly hotter and others in which it cools. These changes are of order several hundred degrees and are accompanied by shifts in brightness. When the effective temperature rises, the star emits relatively more light at shorter wavelengths, while a cooler photosphere radiates more strongly in the red and infrared. Because the radius can also change as the outer envelope expands and contracts, the luminosity variations reflect a combination of changes in surface temperature and area. The net effect is a complex light curve in which the photosphere plays a central role. Interferometric observations provide additional constraints on the extent and structure of the photosphere. By measuring how the brightness of the star varies with baseline length and orientation, these observations reconstruct the angular size and, in some cases, the brightness distribution across the disk. For HR 5171, such measurements show that the apparent radius in the near-infrared is extremely large, consistent with the values inferred from luminosity and temperature when combined with distance estimates. They also reveal asymmetries in the brightness distribution that suggest the photosphere is not perfectly uniform. Some portions of the surface appear brighter or dimmer than others, hinting at large-scale structures or temperature variations. While the detailed interpretation of these patterns involves the convective and pulsational behavior to be discussed separately, the key point here is that the photosphere is extended and structured with observable departures from a simple smooth disk. The photospheric layers also host the partial ionization zones that strongly influence the stability of the envelope, In regions where hydrogen or helium transitions between different ionization states over a limited temperature range, the opacity of the gas can change rapidly with temperature. When a layer of gas in such a zone is compressed, its temperature can rise, increasing ionization and opacity. The increased opacity traps radiation, raising the local pressure and causing the layer to expand again. As it expands and cools, ionization drops, opacity falls, and radiation escapes more easily, allowing contraction. This feedback mechanism underlies some of the pulsations observed in luminous cool stars. In the case of a yellow hypergiant, these processes operate in or near the photosphere, making it a region where energy flow opacity changes and mechanical motions are tightly coupled. The linked behavior of temperature, opacity, and motion gives the photosphere a dynamic character, even though on average it still defines a relatively thin layer from which most visible photons escape. Uncertainties in distance extinction and model atmospheres mean that the exact values of effective temperature and radius for HR 5171A are not pinpointed to a single number. Different studies have produced partly differing combinations of temperature and size that nevertheless agree on the basic picture. The photosphere is very cool compared with hot blue stars, very extended compared with ordinary supergiants, and radiates an enormous amount of energy. Some analyses favor a somewhat cooler and larger configuration. Others a slightly hotter and smaller one, but all place the star among the most luminous and largest yellow hypergiants known. The range of plausible parameters reflects the difficulty of modeling such an extreme extended atmosphere, but it does not alter the qualitative understanding of the photosphere as a vast unstable surface hovering near the limit of radiative stability. From the perspective of the layered description used here, the photosphere marks the boundary between the inflated envelope and the deeper layers where convection and radiation transport energy under higher pressure and density. Outward of the photosphere, the gas becomes part of the partly transparent envelope and farther out the wind. Inward of it, the gas participates in the processes that generate and carry energy from the core toward the surface. In terms of observables, it is this layer that sets the effective temperature, color, and basic spectral type of HR 5171A, and that provides the reference against which changes in brightness and spectral features are interpreted. As the focus moves further inward, attention turns from the average properties of this extended surface to the patterns of motion and brightness that ride upon it, revealing large-scale cells, irregular variability, and time-dependent behavior that add further complexity to the appearance of the star. On the extended surface of the yellow hypergiant, patterns of motion and brightness create a constantly changing scene that reflects the unstable state of the outer envelope. The photosphere does not behave like a smooth static shell. Instead, it hosts large convective cells, pulsations and irregular motions that together produce variations in light and spectrum over timescales from days to many years. In a star as large and luminous as this one, convection near the surface operates on scales that are a substantial fraction of the visible disk. Rising plumes of hotter gas and sinking lanes of cooler gas form cells that span a significant portion of the hemisphere, so that the surface brightness is patchy rather than uniform. These convective structures shift, merge, and dissipate over time as energy is transported outward and as the envelope adapts to changes in internal conditions. Because the radius is enormous, the characteristic timescales for these motions are long, compared with those in smaller stars often running to many weeks or months. The result is a photosphere whose appearance, if observed with very fine resolution, would show bright and dark areas slowly drifting and changing, superimposed on global changes in radius and temperature. Pulsations add an organized component to this behavior. The outer layers of the star participate in global oscillations in which they move inward and outward as a whole, or in patterns that involve multiple zones. These pulsations are driven in part by the same partial ionization zones that influence the envelope structure. During the compressive phase of a pulsation, parts of the outer envelope are squeezed, temperature rises and opacity changes, altering the local radiative force and pressure balance. During the expansive phase, the gas moves outward, cools, and its opacity shifts again. For HR 71, observations of brightness and radial velocity reveal variability on characteristic timescales of many hundreds of days, consistent with the periods expected for such large-scale oscillations in a star of this size and luminosity. The light curve shows both quasi-periodic components, which suggest underlying pulsation modes, and irregularities, which point to a mixture of modes and to the influence of convection and mass loss. Superposed on these global oscillations are shorter-term variations linked to the convective surface patterns. As large cells evolve, they change the distribution of brightness across the disk. When a particularly bright region rotates into view or expands, the integrated light can increase slightly. When a cooler or more obscured region becomes dominant, it can decrease. Because the star rotates slowly compared with its pulsation timescales and convective turnover times, rotational modulation is less regular than in compact, rapidly rotating stars, but it still contributes to the complex variability. Spectral lines formed in the photosphere and inner wind respond to these changes, showing shifts in shape and position as different regions of the surface move toward or away from the observer, and as local temperatures and densities change. Line profile variations over time reflect both pulsation-induced velocity fields and the evolving convective pattern, so that the spectrum carries a record of the dynamic surface. Long-term monitoring of the star reveals that its average effective temperature and radius do not remain fixed. Over periods of several years to decades, the hypergiant has been observed in states that are slightly hotter and more compact, and in others that are cooler and more extended. These changes are inferred from shifts in spectral type colors and brightness, and they indicate that the outer envelope adjusts its structure over time in response to changes in deeper layers. In hotter states, the continuum and certain lines suggest a slightly higher effective temperature, while in cooler states they shift toward values more typical of later spectral types. Because luminosity radius and temperature are linked through basic radiative relations, these temperature changes imply corresponding changes in radius, at least within the uncertainties set by distance and extinction. Thus, the surface of HR 5171 A does not simply oscillate around a single mean configuration. Instead, it moves through a range of states that reflect the long-term evolution of its envelope. This evolution is not smooth. Sudden changes in light curve properties and spectral features at some epochs suggest episodes in which the outer layers reorganize more abruptly. Such episodes may involve changes in pulsation mode adjustments in the structure of the inflated envelope, or shifts in the mass loss rate. For example, an increase in mass loss can alter the density and opacity of the atmosphere, and wind reshaping line profiles and the detailed energy distribution at the photosphere. Similarly, if the outer layers temporarily approach a more unstable configuration, in which the local radiative force very nearly balances gravity, relatively small disturbances can produce disproportionately large responses in radius and brightness. While the precise triggers of such episodes are not always clear, the observational record shows that the hypergiant does not maintain a single steady pattern of variability, but explores a variety of behaviors typical of a star near the limit of stability. Interferometric imaging provides a more direct glimpse of surface inhomogeneities. Reconstructions of the brightness distribution at high angular resolution show that the disk of the star is not uniformly bright. Instead, some regions on the resolved image appear slightly brighter or dimmer than others, and the center-to-limb intensity profile deviates from the simple forms predicted by static one-dimensional atmosphere models. These features are naturally interpreted as manifestations of large convective cells, non-radial pulsations, or both. Because the observations span multiple epochs, they also reveal changes in these patterns, with some bright features fading and others appearing over time. Although the reconstructions carry uncertainties related to limited coverage and modelling assumptions, they nonetheless support the general conclusion that the surface of the star is highly structured and time-dependent. Variability at the surface also links closely to the behaviour of the wind and circumstellar material. When the photosphere expands during a pulsation cycle, the local escape speed decreases and the density scale height increases, making it easier for radiation pressure and shocks to accelerate gas outward. In these phases, the mass loss rate may temporarily increase, feeding more material into the wind and inner nebula. When the photosphere contracts the conditions for launching, the wind change potentially lowering the mass loss rate or altering the acceleration profile. Over many cycles, this coupling between pulsation and wind launching can produce shells or density enhancements at distances corresponding to the mean outflow speed times the pulsation period. In this way, patterns in the surface motion leave imprints on the large-scale circumstellar structure. At the same time, changes in the wind can feed back on the surface by modifying the outer boundary conditions such as the pressure at the base of the outflow. Observers disentangle these linked effects by comparing light curves, radial velocity curves, spectral line diagnostics, and high-resolution images over long timescales. Not all aspects of the variability are fully understood. The light curve contains both relatively regular components and irregular features that do not repeat in simple cycles. Some models favour a combination of several overlapping pulsation modes, including both radial and non-radial oscillations, interacting with convection and envelope inflation. Others emphasize the possibility that changes in internal structure, such as shifts in the location of convection zones, or in the temperature gradient, can alter the pulsation spectrum over time. Additionally, variations in circumstellar dust close to the line of sight can modulate the apparent brightness independent of changes in the photosphere, especially in a system that already produces significant dust through its wind. The available data support the presence of large amplitude pulsations and surface structures, but do not yet define a single definitive pattern that explains every feature. Instead, the variability is best described as a superposition of processes that operate on different timescales and in different layers, with the photosphere serving as the interface where many of them become visible. Despite these complexities, certain regularities emerge. The star shows characteristic timescales of variation of several hundred days to more than 1,000 days, consistent with expectations for pulsations in a hypergiant of its size and mass. It also maintains on average the effective temperature and luminosity expected for a yellow hypergiant, even as it moves within a limited range around those values. The amplitude of brightness variations, while large compared with many other evolved stars, does not reach the extreme outbursts seen in some eruptive variables, and the overall behavior remains within the domain associated with strongly pulsating high mass-extended envelopes. From the standpoint of the layered description followed here, the surface patterns and variability of HR 5171A represent the most external manifestation of the complex dynamics of its outer envelope. They connect directly to the behavior of the inflated layers beneath, and to the wind launched above, translating changes in internal conditions into observable signals in light and spectrum. Moving further inward, the focus shifts from this visible boundary to the inner envelope where temperatures and densities rise, where nuclear processed material emerges, and where the structure of the star transitions from the dynamic outer layers into the more stratified interior that supplies the energy driving all of these surface phenomena. Beneath the extended photosphere and the turbulent outer envelope of the yellow hypergiant lies a deeper region where temperature and density rise steadily and where the structure begins to resemble the layered arrangement familiar from models of evolved massive stars. This inner envelope is no longer directly visible in light, but it supplies both the energy and the processed material that shape the observable surface and the wind. It spans the range of radii between the thin zone where most continuum photons escape and the compact central regions where nuclear fusion proceeds at extreme temperatures. In this intermediate domain, gas is arranged in shells that differ in composition, temperature, and mode of energy transport, and the gradual outward flow of energy from the core passes through each of these shells on its way to the surface. For HR 5171. The thickness and exact boundaries of these layers cannot be measured directly, but theoretical models of stars with similar luminosity, temperature, and mass provide a consistent framework for understanding their general properties. In the outer part of the inner envelope, hydrogen remains the dominant element by mass mixed with helium and heavier elements, in proportions set both by the composition of the natal cloud and by the partial processing that has already taken place. Here temperatures are high enough that hydrogen is fully ionized and the gas is compressed to densities much greater than those in the inflated envelope above. Energy entering this region from deeper layers is carried either by radiation or by convection depending on the local opacity and temperature gradient. Where opacity is relatively low and the temperature gradient is shallow, photons can diffuse outward and carry the energy flux. Where opacity increases, for example, in zones associated with certain ionization states, radiation struggles to transport the energy alone and convection must assist. The balance between these two modes defines the stability and response of the envelope to small disturbances, and it sets the conditions under which large-scale pulsations can develop. Deeper in hydrogen fusion no longer occurs uniformly throughout the envelope. In a massive star that has already spent time as a blue or red supergiant central hydrogen, burning has ended and hydrogen fusion has retreated to a shell surrounding an inner region primarily composed of helium. In such a hydrogen-burning shell, temperatures are high enough for the dominant energy-producing process to be the carbon-nitrogen-oxygen cycle, in which hydrogen nuclei are converted into helium using heavier nuclei as catalysts. This process is very sensitive to temperature, so the energy generation rate in the shell changes rapidly, with small changes in temperature or density. For a star with the luminosity of HR 5171a, the power produced in this shell must be enormous, since it must supply the observed radiative output, as well as the energy required to lift and accelerate material in the envelope and wind. The shell itself occupies only a narrow radial range compared with the overall radius of the star, yet it plays a central role in setting the luminosity and in influencing the structure of the overlying layers. Immediately above the hydrogen-burning shell, the envelope contains material that has been partially processed by this fusion cycle. In the carbon-nitrogen-oxygen cycle, nitrogen builds up at the expense of carbon and oxygen, so that gas that has spent time in the burning region becomes enriched in nitrogen and depleted in some other light elements. Convection and other mixing processes can bring this processed gas outward into layers that now lie within the inner envelope. When such material appears near the surface, it leaves signatures in the observed chemical abundances, and in the case of the hypergiant in Centaurus, Spectroscopic studies indeed find nitrogen enrichment and related abundance patterns consistent with the exposure of carbon-nitrogen-oxygen processed gas. This implies that the inner envelope is not chemically uniform but contains gradients in composition that reflect both the current location of fusion shells and the past history of mixing. The depth to which these gradients extend and the efficiency of mixing remain uncertain and different. Stellar evolution models explore a range of possibilities, but the general presence of processed material in the envelope is well supported. Beneath the hydrogen-burning shell lies the helium-rich core or inner region, where helium fusion may already be underway or be close to ignition. In massive stars at this evolutionary stage, helium burning in the core can begin, while hydrogen continues to burn in a shell above it. Helium fusion proceeds through reactions that combine helium nuclei to form carbon and at higher temperatures oxygen. These processes require temperatures of many tens of millions of degrees and densities far higher than those in the envelope. Although the core itself belongs to the next inward layer, its presence strongly influences the structure of the inner envelope because its mass and energy output set the gravity and luminosity that the overlying shells must support. The boundary between the helium-dominated region and the hydrogen-rich envelope is marked by steep gradients in composition and density, and by changes in the dominant mode of energy generation. Mixing across this boundary is limited but not entirely absent, especially in massive stars where convection overshooting and rotationally induced flows can transport material. The exact extent of such mixing in HR 5171a is not known and remains a source of uncertainty in models of its internal structure. Within the hydrogen-rich part of the inner envelope, energy transport is often dominated by radiation. Photons produced in the core and in burning shells scatter countless times as they diffuse outward through the dense gas. This radiative flux must be carried through regions where opacity varies with temperature density and composition. Where the required energy flux pushes the temperature gradient close to or beyond the threshold for convective instability, convection sets in and alleviates the burden on radiation. In some models of yellow hypergiants, large convection zones extend outward from near the hydrogen-burning shell into the envelope, creating a deep convective mantle beneath the more tenuous outer layers. If such a mantle exists in HR 5171a, it would provide a natural pathway for nuclear processed material to reach the surface and would help to explain some aspects of the star variability. However, the exact topology of convective and radiative zones depends sensitively on parameters such as mass rotation and prior mass loss, so different models may predict somewhat different structures while still reproducing the general observables. The energy flux passing through the inner envelope is enormous. For a luminosity of several 100,000 to around 1 million times that of the Sun, the inner layers must convey far more energy per unit time than in ordinary stars. This high flux steepens the temperature gradient required for radiative transport and brings larger regions close to the limit where radiation pressure becomes comparable to gas pressure and gravity. In such conditions, the envelope tends to expand and inflate, creating the extended structure described in earlier sections. Small changes in the rate of energy generation in the core or burning shells can lead to significant adjustments in the envelope because the system must maintain a configuration that allows the outgoing flux to be transported without gross imbalance. If, for example, the hydrogen-burning shell becomes slightly more luminous, the additional energy steepens the temperature gradient in the overlying layers, which may respond by expanding until a new equilibrium is reached. Such readjustments can manifest as changes in effective temperature radius and surface brightness over timescales comparable to the thermal timescale of the envelope, which for a hypergiant can be of order years to decades. Rotation adds another dimension to the structure of the inner envelope. Even if surface rotation appears slow because the radius is extremely large, the deeper layers may retain more angular momentum, and the star as a whole may rotate significantly. Rotationally induced mixing can transport angular momentum and chemical species between different layers, smoothing out composition gradients and bringing processed material into the envelope. It can also alter the shape of equipotential surfaces, making the star slightly oblate, and changing the local balance between gravity and radiation as a function of latitude, for HR 171. A direct measurements of internal rotation are not available, and models must rely on plausible assumptions based on massive star evolution in general. Nonetheless, some degree of rotational mixing is likely, and it contributes to the presence of fusion products in the inner envelope, and to the complexity of its stratification. The efficiency of this mixing remains one of the less well-constrained aspects of the structure. In the deepest parts of the inner envelope just outside the formal core region, densities and temperatures approach values where matter behaves in a way that is more strongly influenced by electron degeneracy and by subtle changes in the equation of state. These inner zones help to set the overall size of the core and the stiffness of the boundary between core and envelope. The envelope must adjust to the core radius and mass, and the strong gravity at this interface anchors the stratification of the overlying layers. The precise location of this transition is uncertain for HR 5171a because it depends on the star initial mass, on how much mass has already been lost, and on details of mixing and burning history. Observational constraints such as the current luminosity, effective temperature, and surface abundances narrow the range of plausible models but do not select a single structure. Even so, all acceptable models share the key feature that the inner envelope contains fusion products and steep gradients in composition above a dense energy-producing core. From the standpoint of the layered description used here, the inner envelope serves as the bridge between the observable outer star and the core, where nuclear reactions directly generate the energy that ultimately emerges as light and drives mass loss. It contains the shells, where hydrogen burning continues in a narrow zone, where helium-rich material begins to accumulate or burn, and where processed gas is stored and sometimes mixed upward. It also sets the conditions under which the outer envelope can inflate, pulsate, and lose mass. As attention moves one step further inward, the focus shifts to the core itself, where temperatures and densities reach their highest values, where the detailed balance of nuclear reactions takes place, and where the overall stability and future evolution of the hypergiant are decided in physical terms. At the center of the yellow hypergiant, far beneath the extended photosphere and the stratified inner envelope, lies the core, a compact region in which nuclear fusion proceeds at temperatures of many tens of millions of degrees and densities, far higher than anywhere in the surrounding layers. This core is the physical engine that supplies the energy required to support the weight of the overlying gas and to power the enormous luminosity observed at the surface. In a massive evolved star like HR 5171a, the core no longer burns hydrogen uniformly throughout its volume, as a young main sequence star does. Instead, hydrogen burning has withdrawn into a shell, and the central regions are primarily composed of helium and heavier elements. In many models of stars with similar brightness and surface temperature, helium fusion has already started in the core, or is very close to doing so, with reactions that combine helium nuclei to form carbon, and at higher temperatures oxygen. The precise state of burning in the core of this particular hypergiant cannot be observed directly, so there is some uncertainty about whether helium fusion is firmly established, or still in its earlier stages. but there is broad agreement that hydrogen burning in a shell and a helium-rich interior together underpin the current energy output. Within the core, pressure arises from a combination of hot gas and radiation. Gas pressure comes from the rapid motions of particles, mainly ions and electrons, while radiation pressure is the momentum carried by photons streaming through the matter. In an object as luminous as HR 5171, a radiation pressure forms a large fraction of the total support, especially in the deeper layers where temperatures are highest. Gravity acting inward on the mass of the core and envelope is balanced by these pressures, so that on average the star remains in hydrostatic equilibrium. This balance is not static in a strict sense because nuclear burning gradually alters the composition and temperature profiles, and the envelope responds over thermal timescales. But at any given moment the core adjusts its structure so that the inward pull of gravity is matched by the outward push of gas and radiation pressure. If the core were to generate substantially more energy, then the overlying layers can transport the resulting excess, would steepen temperature gradients and drive expansion. If it produced significantly less, the star would contract. The present state of the hypergiant reflects a configuration in which the core luminosity and the transport capacity of the envelope are approximately matched, even if small imbalances drive the slow structural changes and pulsations observed at the surface. Energy generation in the core and in the surrounding hydrogen-burning shell is highly sensitive to temperature. In the hydrogen-burning shell, the carbon-nitrogen-oxygen cycle rate rises strongly, with even modest increases in temperature, while in a helium-burning core, the triple alpha reaction and subsequent reactions to form carbon and oxygen also depend steeply on temperature. This sensitivity means that small perturbations in temperature or density can cause noticeable adjustments in energy output. However, the core does not respond in an unstable runaway manner under current conditions because expansion tends to cool overheated regions and contraction tends to heat under luminous regions, providing a stabilizing feedback. The presence of a hydrogen-burning shell around a helium-rich interior introduces an additional layer of coupling. Changes in the core influence the shell by altering the gravity and luminosity at its base, while changes in the shell affect how much energy the envelope must carry and how the star appears at the surface. In this way, the core and shell together determine the total luminosity that inflates the outer layers and drives the wind. The structure of the core itself is likely convective over a significant fraction of its radius. In a region where energy generation is concentrated, and where opacities are high, radiative transport alone cannot carry the required flux without producing a temperature gradient steep enough to make the gas convectively unstable. Rising and sinking motions then develop mixing material within the core, and maintaining a nearly uniform composition over the convective region. In a helium-burning core, this convective mixing distributes the products of fusion such as carbon and oxygen throughout the core volume rather than leaving them confined to narrow shells. Above the convective core, a boundary separates the helium-dominated interior from the hydrogen-rich envelope. The sharpness of this boundary and the extent to which material crosses it depend on phenomena such as convective overshooting internal waves and rotationally induced mixing. These processes are difficult to model precisely, and their efficiency in HR 5171A is not directly known, so the exact profiles of composition and temperature in the transition region remain uncertain. Nevertheless, all reasonable models include a compact core with higher mean molecular weight and a surrounding envelope with lighter composition, forming a stratification that influences both the star current structure and its eventual evolution. Neutrino emission provides an additional channel for energy loss in the deepest parts of the core. At the high temperatures and densities present, their processes such as pair production and plasma interactions can generate neutrinos which interact only weakly with matter and escape almost freely. These neutrino losses remove energy without contributing to the outward radiative flux, and therefore must be balanced by higher nuclear burning rates if the core is to maintain its structure. In the present stage of HR 5171, neutrino losses are important but not yet dominant compared with the radiative luminosity. So the overall picture remains one in which nuclear fusion in the core and shell supply both the radiated light and the pressure support against gravity. As the star continues to evolve, neutrino losses are expected to grow in importance in deeper phases, but that lies beyond the immediate focus on the current structure. The mass contained in the core is a substantial fraction of the total mass of the star, but its exact value is not directly measured. Initial mass estimates for HR 5171 range over several tens of solar masses, and the star has already lost a significant amount of material through winds and outflows. The present-day total mass is therefore lower than the original, and the core mass reflects both the initial central concentration and the history of nuclear burning and mixing. Evolutionary models that match the observed luminosity, surface temperature and abundances typically require a core that contains several solar masses of helium and heavier elements, surrounded by a hydrogen-rich envelope whose mass is smaller than in earlier phases. However, uncertainties in distance extinction rotation and mass loss history allow a range of core and envelope mass combinations, so any specific numbers remain model-dependent. What is robust is that the core mass is large enough to sustain the observed luminosity and to keep the star near the upper part of the temperature-luminosity diagram, placing it close to the limit where radiation pressure challenges gravity in the envelope. The energy balance between the core and the outer layers imposes constraints on how the star can respond to disturbances. If the core output increases slowly, the envelope can expand and cool until the radiative flux at the surface again matches the interior supply. If the output decreases, the envelope can contract and heat, raising the surface temperature and altering the balance of radiation and gas pressure. These adjustments occur on the thermal timescale of the envelope, which for a hypergiant is long enough that changes appear gradual on human timescales, but short compared with the full nuclear timescale of the core. The observed long-term variations in effective temperature and radius of HR 5171A are consistent with such envelope readjustments driven by changes in the internal structure, even though the details of how core luminosity and shell burning fluctuate are inferred rather than directly measured. In this sense, the core acts as a slowly varying power source, and the envelope acts as a responsive but massive regulator that transforms core energy into observable light and into work done on the outflowing wind. Stability of the core itself depends on the balance between gravity, pressure, and energy generation, and on the composition profile built up by nuclear burning. As hydrogen continues to burn in the shell, and helium accumulates in the core, the central regions become denser and more compact. Helium fusion and subsequent burning stages modify the equation of state and the density profile. As long as the core pressure, including both gas and radiation components, can balance gravity, the structure remains in quasi-static equilibrium. When critical thresholds in mass composition and energy loss are approached, the core can become prone to more dramatic changes in radius and temperature. But for the present hypergiant stage, the evidence points to a core that still supports the envelope without rapid, catastrophic changes. The constraints from luminosity and spectral type indicate an interior that has advanced well beyond the main sequence, but has not yet reached the terminal stages of collapse. From the viewpoint of the layered description, This core region is the deepest layer reached in the analysis of HR 571a. It is the site where nuclear reactions convert mass into energy, where composition stratification is established, and where the fundamental balance between gravity and pressure that defines the star is set. Everything observed in the outer envelope, the photosphere, the wind, and the circumstellar nebula, ultimately traces back to the conditions and processes operating here. Once the core structure and energy balance are understood in broad terms, the final step is to place this configuration along the sequence of massive star evolution, considering how a star that begins as a hot compact object on the main sequence moves through red and yellow supergiant phases, and which broad evolutionary paths remain physically possible given the core and envelope structure now present in this hypergiant. The internal structure described in the preceding layers places the yellow hypergiant at a well-advanced point in the life of a very massive star. It no longer burns hydrogen in a central core as a young compact object would. Instead, hydrogen fusion now proceeds in a shell surrounding a helium-rich interior, and the outer envelope has expanded and cooled into the unstable inflated configuration that gives the star its present appearance. From the outside, this stage is recognized as the yellow hypergiant phase. From the inside, it is characterized by a powerful core and shell luminosity, a large helium-dominated center, and an extended hydrogen-rich envelope that is close to the limit of radiative stability. Together, these features define a star that has moved far from the main sequence, and that stands in a transitional region of massive star evolution. The earlier path that leads to this state begins when the progenitor forms in the dense gas of the Centaurus arm as a very massive hot main sequence star. In that initial phase, hydrogen fusion in the core supplies all of the luminosity, and the star appears as a blue object with a compact radius and a high surface temperature. Over a span of only a few million years, the central hydrogen gradually converts to helium. As the hydrogen abundance in the core falls, the core contracts and heats, and the outer layers respond by expanding. Depending on the initial mass rotation and mass loss history, the star may pass through a red supergiant phase, where the envelope becomes even cooler and larger, or it may evolve more directly through the yellow supergiant region. In some models, massive stars move back and forth in effective temperature at roughly constant luminosity, tracing loops across the temperature-luminosity diagram as their internal structure adjusts. The present configuration of HR 5171a as an extremely luminous, cool but not fully red hypergiant is consistent with a star that has already left the main sequence and perhaps passed through cooler or hotter stages before settling temporarily into its current state. In the present phase, the core and shell burning supply an enormous energy flux that must be carried through the envelope. The high luminosity inflates the outer layers and drives the strong wind and mass loss described earlier. As hydrogen shell burning continues and helium builds up in the interior, the core gradually contracts and heats further. This slow contraction increases the central temperature and density, preparing the conditions for more advanced fusion stages. At the same time, mass loss steadily reduces the mass of the envelope. The combined effect of a growing core and a shrinking envelope is to alter the balance between gravity pressure and radiation throughout the star. In many evolutionary calculations, such changes eventually cause the envelope of a yellow hypergiant to contract and heat, moving the star back toward higher effective temperatures while maintaining a similar luminosity. In that case, the star can evolve into a hotter blue supergiant or a luminous blue variable-like object with an increasingly stripped envelope and a wind that may become faster and less dense per unit volume. Whether the hypergiant in Centaurus already stands near the point of such a transition or still has a longer interval in the present state, remains uncertain, because the exact timing depends sensitively on the current mass, the detailed structure of the core, and the time-integrated mass loss rate, none of which are directly measured. If the envelope does contract and the surface temperature rises, the star would shift in spectral type, and its wind and circumstellar environment would gradually change character. Over longer timescales, as helium burning in the core proceeds and produces carbon and oxygen fusion, can move on to even more advanced stages in layers within the core. Carbon, neon, oxygen, and silicon burning can occur in nested shells, each operating at higher temperatures and over progressively shorter timescales. These deep processes do not immediately alter the observable classification, but do change the mass composition and structure of the core. In general, for very massive stars, the core eventually builds up a central region, dominated by iron group elements, which cannot release energy through further fusion. When the mass and structure of this iron-rich core reach a critical configuration, the core no longer supports itself by thermal and radiation pressure alone, and it collapses under gravity. The precise core mass at collapse and the state of the envelope at that time depend on the integrated history of mass loss and mixing. These deeper burning stages are not yet directly accessible to observation in HR 5171a, and their exact onset times remain part of theoretical models, rather than firmly established facts for this specific star, but they represent the general sequence expected for stars in the same mass range. The fate of the core collapse phase also depends on the remaining mass of the envelope. If the envelope is still substantial when collapse occurs, the resulting explosion manifests as a bright core collapse supernova of a type that retains hydrogen in its outer layers. If mass loss has already stripped most of the hydrogen and even helium from the star, the explosion may appear as a different spectroscopic type with lines from heavier elements dominating. In some cases, if the core is very massive, much of the matter may fall back after the initial collapse, and the explosion may be weaker, with less mass ejected. The compact remnant left behind can be a neutron star or a black hole depending on core mass and equation of state. For HR 5171a, the present data constrain the luminosity, effective temperature, and surface abundances, but do not uniquely determine the future envelope mass or the precise type of eventual explosion and remnant. Instead, a range of outcomes remains possible within the broad framework of massive star evolution, all of which involve core collapse but differ in detail. The timescales associated with the remaining life of a star in this phase are short in galactic terms, but long compared with human lifetimes. The entire post-main sequence evolution of a very massive star can span only a few million years, with the yellow hypergiant stage occupying a fraction of that time, possibly of order tens of thousands to a few 100,000 years. Within this interval, variations in mass loss and structural adjustments can continue to shift the star through different parts of the temperature-luminosity diagram. Observationally, decades of monitoring capture only a small segment of this evolution, during which the star may show cycles in brightness and temperature, and changes in wind strength without moving dramatically in its overall evolutionary state. Even so, long-term changes already seen in spectra and light curves suggest that the outer layers of HR 5171a respond measurably to the internal evolution on timescales of years to decades. In the context of its environment in the Centaurus arm and the GUM-48d complex, the evolutionary state of the hypergiant has direct consequences for the surrounding gas. As long as it remains in the yellow hypergiant phase, it continues to supply a dense, slow wind that enriches the local medium in nuclear-processed elements and feeds the circumstellar nebula. If it evolves toward a hotter, more compact phase, the wind properties change and the radiation field becomes harsher, potentially ionizing and shaping the nearby gas in new ways. The eventual core collapse and explosion when it occurs will inject a large amount of energy and heavy elements into the interior of the evolved ionized region, generating shock waves that propagate through the circumstellar shells and into the molecular clouds at the edge of the bubble. The detailed pattern of this interaction depends on the exact distribution of circumstellar material at the time of collapse, which is itself determined by the preceding centuries to millennia of mass loss. In this way, the internal evolution of the star connects tightly to the future structure and composition of the surrounding nebula. From a broader perspective, HR 5171a exemplifies a short and rare stage in the life of very massive stars in galaxies like the Milky Way. It stands as one of only a small number of known yellow hypergiants, occupying a narrow region of parameter space, where an enormous luminosity, a swollen envelope, and strong mass loss coexist. Its location in a star-forming complex in the Centaurus arm its association with an evolved ionized bubble, and its complex circumstellar environment all align with theoretical expectations for this evolutionary stage. At the same time, uncertainties in its exact mass internal structure and binarity illustrate the challenges of fully characterizing such extreme objects. Observations at many wavelengths continue to refine the picture, but some aspects of its future path remain open, bounded by the general framework of massive star evolution, but not yet fixed to a single detailed scenario. Within the layered description followed throughout the core and surrounding shells, define the deepest structural layer, and the evolutionary pathways they support form the temporal layer that accompanies the spatial structure. Energy generated in these inner zones travels outward through the inner envelope inflated outer layers, photosphere and wind shaping every observable feature, from large-scale nebulae to small-scale surface patterns. Matter processed in the core, and shells moves outward through mixing and mass loss to build the circumstellar environment and eventually to join the interstellar medium of the Centaurus arm. Seen in this light, the yellow hypergiant at the heart of the GUM-48d region is both a single specific object and a node in the wider cycle of mass and energy in the Milky Way, connecting deep nuclear reactions to the glowing gas and dust in its surroundings.